Hello and welcome to another video. In this one, we're going to be going over Advent of Code Day 5. And I feel like Day 5 is one of the first where the difficulty gets ramped a little bit. And so we're gonna go over the parts that I think are tricky and how I solved it. So let's jump into it. Okay, so first we're going to start with the problem description. Again, I can't show the actual one, so I have made a simplified version of it here. And in, let's actually open up the parsing as well, because that way we can kind of see an example. So our puzzle input this time is a list of like airplane seat IDs, and they're specified in this kind of weird format, which is comprised of F's and B's. Now the first 7 characters of this are only F's and B's, and this tells you where on the airplane the row is. And F refers to front and B refers to back. We'll actually talk a little bit more. I have a little diagram that makes this make a little bit more sense, but basically coming from left to right, you decide which half of each part you're considering based on the F and B. So if you've worked with a like binary search algorithm, it reads a lot like, you know, the reverse of doing a binary search. I'll actually show you the trick that I jumped to first. I didn't even try the binary search because I knew how complicated that was going to be. But there's actually a clever trick that makes this a lot simpler. But let's jump into the diagram. Yeah, the first 7 are the row, and the last 3 are the column. So it goes right and left to pick the column. And here's a little diagram that I drew. In this diagram, we're looking at that same string that we had before: front, back, front, and right, left. And you'll see I've numbered the rows from 0 to 127. I haven't bothered doing the intermediate rows, and I've labeled the columns 0 to 8. So let's talk about the row first. And so what the F tells you, so first you would start by looking at this F, and what this F tells you is that you can eliminate this chunk here. I realize red and green are maybe not the best choice for colorblind, but anyway, you can pretend like there is, a differentiator here. So this back part is now eliminated, so it must be in this chunk here. And then we see the next F, which eliminates another half, and so it must be in this chunk here. We see a third F, which eliminates this half here, and so it must be here. Then we see a B, which eliminates the front half here, because it must be in the back half of the remaining stuff. And eventually you see it kind of narrows down into exactly one number, and so this happens to be row 8. And we see a similar approach for the column determination, but instead of doing backwards and forwards, it's right and left, and it bounces between 0 and 8. So you can see this one we have RRL, so R eliminates the left-hand side of the plane, and so it must be the right-hand side. We get another R, which again eliminates the the third from the left quarter of the plane, which means it has to be in one of these. And then finally we eliminate row 7, and oh, this is off by 1. Sorry. This is supposed to be 7. My bad. So sorry. The last L eliminates row 7, and which means that it must be column 6. Once you're given both the row and column, the seed ID is the row times 8 plus the column. And so I guess we'll jump into the parsing. So I noticed, or when I saw this and when I saw all of the numbers being involved, like 0, 127, 8, and the examples also had 64 and 32, I recognized all of those as powers of 2, which kind of gave me a little thought in my head that, oh, maybe there's like some trick with binary numbers here. So what I did, if you watch the stream live, this is what I immediately jumped to. I took the chunk of this string that was just the B's and F's, and I made a string for that. And I immediately tried converting that to base 2. So I just did something like s.replace B with 1 and .replace F with, actually let's do it the wrong way first. This is actually what I did on stream. I did the wrong way first. Replace F with 1, and that gives us a binary string. And if we do int on that with base 2, so you can select the base in Python by passing the second argument to the int function, and that converts it directly to an integer for us. If we do 57 times 8, oh, maybe this one was right. No, Yeah, this one was wrong. So this plus our row ID here, RRR, would have given us 7. So that would not have worked. So plus, I guess we can do the other half of it. Well, let's get this right first. So if we look at part 1, I think I wrote down what that one is. Yeah, that one's supposed to be in row 70, but I got row 456. So let's try. Or wait, what did I get? I got row 57. We try and flip that instead. So if we set B to 1 and F to 0, you'll see that we get row 70. So that's how I was able to get the row out of here. What you could do, and what I saw a lot of people that didn't catch on to this trick to, is write a loop that, you know, slowly narrowed in the bounds by dividing by 2. It was really tricky though, because you have to be very careful about off by 1 errors and make sure you're using integer division. I'm actually not going to show that because I didn't write the code for it, and we're just going to proceed with this little trick instead. The other part of this is getting the column, and the column I determined in a similar way. So let's actually take RRR. Well, let's take one of the more interesting ones, RLL. So S2 equals this, and if we do int of S2.replace R with 0 and L with 1, that actually gets us the wrong one. I didn't mean to do the wrong one. But again, like I was trying to go fast, and oh, this is supposed to be int 2. Yeah, so this is how you get the column ID out of this, you know, seat part here. And combining those two together, so let's say we took this one, entire one here, seat equals this, and we can slice a different a part out of this. So we can do for the front part, the row ID, we can do row equals this, but instead of S, we're doing seat. And I'm going to do a slice to -3. So this is going to eliminate everything except for the last 3 characters. And you can see we get the row as 102 here. And we can get the column as int, copy this guy here, as seat -3 colon. So this is from -3 onwards. And so you can see we get row 102 and column 4. And if we do row times 8, oh man, I did that same typo on my actual solve. That cost me so much time. But yeah, if you do row times 8 plus column, you get this answer, 820. Now, another hint that you might notice here is that this times 8, this is another power of 2. And in fact, it is 2 to the 3rd. And if you worked with binary numbers, and anytime you multiply by 2, you just shift the bits over 1. So multiplying by 8 is a bit shift over to the right of 3, which actually lines up exactly with how this is formatted. You can see you can imagine there's a padding of 3 zeros here as we left shifted this. So we actually don't need to parse the row and the column separately. We can do all of them at once. So we can do that with int seat, and we got to couple both of these replaces here. Fortunately, these letters don't overlap, so we don't have to do anything special there. But if we copy that one, and we copy this one, and replace that with int 2, and you can see that we get exactly the same number here. So this is how I did my parsing, which simplifies the problem a lot, and might be something that, you know, if you didn't get this trick, you might have spent a lot more time working on this problem. But let's actually write out the code for this. So oh wait, this is part 1. Let's write out the code for this. So our return value is going to be a list from type A import list, because I forgot to import that. And for line in s.splitlines, again, splitlines is pretty helpful in this in that it eliminates all the white space around our lines here, and we don't have to worry about the trailing new line at the end. And let's see, we can do seat equals line dot replace. I'm going to do this in 2 lines just because it's going to be easier to read. So do line, oh, also we're off screen, so let me get that on screen for you. And we do the second set of replaces here as well. So let's just do line. That way we can use the same set of variables all the way through. And finally, ret.append int of line in base 2. Return ret. And so if we run this, parsing.py, you'll see that we get the expected result there. So I would say that most of this problem was spent on parsing, and then the actual computation part of this was pretty straightforward. But we'll do the computation part of this anyway. So this is the parsing. This is how I did the parsing. You could do this with a complicated loop instead. All right, so let's switch to part1.py. And again, we're using the input that's already parsed here, so we don't have to do any reparsing here. And what part 1 asked us to do is to find the maximum seed ID. Now, if you did the parsing, this part was super easy. It was just return max of input. Max is a function which is a built-in in Python, which just gives you the maximum value. If you didn't know about maximum, though, you could have implemented maximum by hand. So one way to implement compute manual. One way to compute max by hand is by setting maximum to 0, and then for n in input, and do something like maximum equals max. Well, again, I'm using max here. You could say if n is greater than maximum, then maximum equals n. And that would be how you would manually write this out. Compute manual. And you can see that we get the same result there. This actually helps us visualize the ON a lot easier. So this is, ON. And this is O1, so overall this is ON. You might not know that from the max function, although you could intuit that it has to look at every single value at least once. So it must be at least O of n, and there's no reason for it to look at them more than once, so it has to be ON. But anyway, that's part 1. Part 1's pretty straightforward. Oh, what did I just do? Oh, I did Windows key desktop. Okay, that's not what I meant to do. All right, let's open up part 2. In part 2, I've actually generated my own sample input. So if you want to take this as like a test case, there wasn't actually a test case given for part 2, so I made one of my own. And this one represents the numbers between 900 and 909. Of course, it is missing 906, which is the answer to this problem. So we should expect to get 906 at the end of this. The way I actually generated this is by using, kind of the reverse of this replacement. I replaced ones with R's and L's and F's and B's instead. But anyway, we're working with the pre-parsed input here to save the parsing code here. And this one was actually kind of tricky for me. I thought of not the greatest solution to this, but then, my second pass at solving this was a little bit better. So I'll show you both passes at how I did this. I first figured out that the maximum ID is going to be all of these being 1s and all of these being 0s. And if you've worked with binary, you'll know that the maximum for n bits is 2 to the n minus 1. So if we do that in Python, 2 raised to the 10 minus 1 means that the maximum that we could see in this, in the seed ID is 1023, and the minimum is just going to be 0. So if we create a range of all the possible inputs, say that all inputs equals, and I actually used a set here, a set from a range from 0 to 1024 non-inclusive. This is range does not include the value. And actually, you can, if the initial value is 0, you can omit it. So this is a set that contains the values from 0 to 1023. And then what I did is for n in input, I discarded that from all inputs. So I just did all inputs dot discard n. And then this left me with all of the seats that were unoccupied. So we were looking for the one unoccupied seat that had 2 seats next to it. And so what I did from that is I looped over the remaining inputs. So I did for remaining in all inputs. And in this case, I looked for something that was, that the previous number was not in there and the next number was not in there. Which actually we'll see if we think about it the other way around, we actually solve the problem a lot easier. And so what we do for that is if remaining. So if it's in this all input set, that means that it wasn't, or that it's occupied. So if remaining -1 not in all inputs, and remaining +1 not in all inputs, then we can return remaining. Arrays not implemented. Or arrays, we were doing assertion error unreachable, right? Unreachable. And if we run this, Python 3 part2.py, yeah, we get 906, which is our missing value here. So this is one way to do it. This is more complicated than it needs to be, but this is how I approach the problem. There's a little bit simpler one. Compute, which uses the same approach, but it's slightly simpler. I actually used this in my SQLite solution because it made the problem a lot easier. So what you can do here is make a set out of the inputs. So all inputs equals set of input. Note here that this is kind of the opposite of this problem here. And one property that I noticed is if you see a number and you see a number that's greater than you that's missing and 2 greater than you that is present, then you know you found your missing seed ID as the middle one. So that's kind of flipping this original logic in a different way. So for n in all inputs, if n+1 not in all inputs and n+2 in all inputs, then we know our answer is n+1. Raise assertion error unreachable. Another solution that I saw to this was just printing out all the numbers and then like manually looking through them and finding the particular value. There's also another trick where if you sum all the numbers between 1 and n, you get n+1 over 2. And then you could subtract out the minimum value and from the maximum value and figure out exactly what's missing there. I guess we could try and attempt that. I haven't really thought about that one though. Print compute simpler. So this should also print 906. Let's try and do the n+1 over 2 trick. Compute mathy trick. And so what we're going to do is we are going to get the max. We can actually compute the min, max, and sum as one loop. That way we don't do as much work. So we do min equals, or minimum equals -1. And maximum equals, you know, some number that's... actually, we want to pick a big number for minimum and a small number for maximum. So we know 1024 is bigger than the possible biggest value, and -1 is smaller than the smallest possible value. And we want total to be 0. That'll be our running sum. And so we can do for number in input, minimum equals min number minimum, and then maximum equals max number maximum, and then total plus equals number. And then at the end of this, we should be able to do n+1 over 2 of maximum. So expected max sum equals maximum times n+1 times maximum plus 1 divided by 2. And we'll actually do you know, float division here, even though we probably want integers, but I just want to make sure that we're not accidentally introducing decimals here. And expected min sum equals minimum times minimum plus 1 over 2. And then if we do, we should be able to do return. Actually, we will do integer division because we know this has to be. We will do return total minus, or expected max sum minus expected min sum minus total. And that should give us a result as well. Compute mathy trick. Does that work? 6. Well, that's not quite right. Let's see what these values came out to. Minimum is 900. Maximum is 909. So expected max sum is that. Oh, you know what? It's supposed to be not inclusive, so this should have been -1. And this should have been -1 + 1, which -1 + 1 cancels out. So that should give us our expected value. The reason is we're subtracting out all the ones that didn't exist. And there we go. Now we get the right value. But let me talk about the ON of each of these three solutions. So this is ON here. This is also ON. This n is slightly bigger than, or these n's are slightly bigger than your total data, but it's not a full factor larger. And since they're parallel to each other, they don't add. They're just, they're the same. ON plus ON is ON. So overall, this one is ON. And of course, if we looped over all of the inputs there and we loop over all of the inputs here. Oh, also, I guess it's worth mentioning this is also ON, building this set here. This is also ON space. This one, again, ON time and ON space, and this is ON time, and this inner part is O1, so overall this is ON time and ON space. Same with this one here. This last one, we do save a little bit on space. Our space is actually constant here. We don't need to store any other special values, and this loop is ON. Oh, you can't see that because it's not on screen. Let me put this on the other screen. Part2.py, there we go. Yeah, so overall for this bottom one, the space is constant, but the runtime is ON. But anyway, this one I felt was a big step up in difficulty, so it was a lot harder than the previous days. But here's my solutions for part 1 and part 2, but I think the parsing was actually the tricky part. Anyway, thank you for watching. I'll see you again for day 6.